last time we saw this quotient functor
from this pre-order to partial order. Okay, so you consider one pre-order, like for example this one, this P, the example that we have on the screen, P is equal to ABC, where the relation is the diagonal union AB, AC, BC and CB. So B and C are equivalent over here, right? So basically one diagram looks like this is P. I am writing this as P. B and C are more or less, they are equivalent, and then whatever is above, that is bigger. Yeah, so A is smaller than B, A is smaller than C, B and C are at the same level. The corresponding partial order reflection, what would that be? It will be A and then B identified with C. Okay, so B is identified with C. So now that's the vertical thing that we have, like there are only two elements. Now if you ask a simple question, simple question which is a categorical question, that whether P has a least element, like P has an initial object. Does it have an initial object? What does it depend on? I mean, you can't, that's not an answer to this question. Does P have an initial object or not? It doesn't, it's either yes or no.
It's not necessarily true. I mean, not every partial order.
I am saying this particular P has an initial object or not. Somebody, what is an initial object?
Are you talking about the category of partial orders?
I am not talking about the category of partial orders. I am talking about one particular pre-order thought of as a category. This picture, A, B, C.
Yes, sir.
Does it have an initial object?
Yes, sir. Yes, sir.
You are saying yes. Who else says yes? Yes. Too cold to raise your hands. Fine. And other people don't think there is an initial object? Where does the property fail? A comma B and? How many morphisms are there between any two objects? More than one morphisms between any two objects? Which two objects have got more than one morphisms? So there is a morphism from B to C, there is a morphism from C to B. Where are two parallel morphisms? No. So yeah, I mean, you were trying to contradict the definition of a pre-order itself. This is a pre-order. I am asking you, does it have an initial object? And you did not raise your hand. So why do you think there is no initial object? What's the meaning of an initial object?
I is an initial object
If
singleton.
if it is singleton. So there should be a less equal sign, or there should be only one arrow from A to something. Yeah, I mean, if A is an initial object. So is it true? A to A there is one arrow. Yeah, AA is in the category, AB is there and AC is there. Okay, so there are A is indeed an initial object in this category. And what about the corresponding Posetel reflection? Does there exist an initial object in that category? Yes? A itself. Now, does that category, the second one, have a terminal object?
Yes, sir.
Yes, what is the terminal object?
The equivalence class of B.
Equivalence class of B and C. Does the original pre-order have a terminal object? No? No? B and C are both terminal. See, there is a unique morphism to B from A, there is a unique morphism from B to B, and there is a unique morphism from C to B. So therefore, B is a terminal object, C is a terminal object, and we have seen that any two terminal objects are isomorphic up to unique isomorphism. So that is also true, B and C are isomorphic. Okay, so both of these categories have got similar properties. Even though they have different number of objects, I mean at least the properties that we know of right now. Yeah, we just know initial and terminal object, but both of them have got the same property. Both of them have initial objects, both of them have terminal object. So this kind of similarity between properties, irrespective of how many objects there are, this is called equivalence of categories. So equivalence of categories is not a bijection per se. Yeah, it doesn't ask you that for this object in this category there should be another object and that should be a perfect one-to-one correspondence. That perfect one-to-one correspondence we'll call a category isomorphism. But in order to freely send properties from one category to another category, you need a slightly weaker notion, and that is called categorical equivalence. So just like these two categories are equivalent. Yeah, these two pre-orders are equivalent because even though they have different number of objects, yeah, they have similar properties. So let us write this down. In order to understand an equivalence, we need one more concept. Yeah, and I'm going to motivate that by saying this. So suppose C and D are categories and F and G are two functors, two parallel functors. Parallel means their domains and codomains are the same, are functors. Our original idea, like original difference between category theory and set theory is what? That we don't have to rely on any, like there is no boundary. The collection of all small categories also forms a category with respect to all functors. Now we are talking about all functors which are parallel, and now we are asking, can those functors, parallel functors, be thought of as objects in a certain category? Okay, the notion of object is changing. We have categories C and D, then we have objects there. Now we are asking what were the morphisms? The morphisms were functors. Now we are treating a functor as an object and we are asking what is a morphism. Yeah, are functors. Then a natural transformation alpha from F to G is given by the data of, okay, before I complete this statement, I want to emphasize on the word natural. Okay, whatever is happening here is natural in the sense that the data that we are going to choose is coherent. It is the most obvious choice that we would do. Now, I don't want to give you the definition directly, but I want to make sure that you understand what's happening really. What will happen, like right now, if there is an object A of category C, then how many objects do you know in category D?
As many as you see.
No, I am saying I know object A exists in category C. Now, do you know any specific objects, like related objects in category D? FA and GA. So, FA and GA. However, there are two different objects. What we need, now there is a sense of direction, okay? Look at this. Alpha is a natural transformation from F to G. So therefore, what we need is a choice of map, choice of a morphism from FA to GA. Okay, that is the data. And it should also behave nicely with respect to the morphisms that we have. And we will look at that. So data is this coherent collection of morphisms. So it's a data of morphisms alpha sub A from FA to GA in D, indexed by objects A of C. So basically we have got lot of morphisms in category D, and each such morphism has a corresponding indexing element coming from objects of C, such that, so this is the data, and then satisfying the following commutative diagram for each morphism F from A to B. Okay, so I am going to write this down in a very specific manner, and that will help you remember what we are doing. So this is happening in C, a morphism F from A to B. Now corresponding to that we have FA, corresponding to A we have FA, we also have GA, here we have FB and we have GB. These are the objects in D. Now we have said that there is a data of morphisms alpha A from FA to GA, there is a morphism given by this data alpha B, and vertically we have the morphisms induced by the functor. The functor is FF, and the functor gives you FF and GF as morphisms from FA to FB and GA to GB. And what we are asking, that this diagram should commute. Okay, so this is what a natural transformation constitutes. So I mean, let me write this: GF composed with alpha A is equal to alpha B composed with FF. This is the commutativity. So you can start at FA and end at GB, and there are two different ways to go from FA to GB, either via GA or via FB, and those two ways are the same. That is the meaning of a commutative diagram. Okay, so this is the data. So the data, I mean, why it is called a natural transformation? Because you are not just choosing one morphism. You can't just make one choice and then hope that it can be extended to a coherent choice of morphism. Here we are making so many choices. If C happens to be a very large category, like the category of sets, then we are making so many choices at the same time. Now, in general, if this data in category C and category D is too big, then we can't make these choices. infinitely many choices have to be given by a rule. And once there is a rule, then there is a naturality. And that's what this name signifies. It's a natural transformation from one functor to another. Any questions?
I mean, we can't define a natural transformation by.
I'm not saying we can't define a natural transformation. We can, but it has to be given by a certain rule.
Yeah, I mean, for the natural transformation which we attach when you given by certain rule,
Mhm.
there might exist natural
There can exist anything,
Yeah.
but if you can't access it, what's the point?
So that's what like constructible. So
I'm not talking about constructibility. Well, let us look at some examples, and if you think it is not natural, then let me know. Okay. So, for example, we have seen. I'm asking you a simple question. Suppose A is a set, and PA is its power set. Does there exist any natural function from A to its power set? Singleton. Okay. Now we are going to say that Singleton map is a natural transformation. Okay. So we have to ask from which functor, like what are the categories? The categories C and D are both the same. They are just the category of sets. What are the functors? I said a morphism from A. Look at this alpha A. Yeah, the Singleton map is the alpha map. It is going from FA to GA, A to PA. So what is the thing that is giving me A? What functor will give me A when applied on A? Identity functor. Oh yes, I forgot to mention something. Yeah, what will happen? Oh yeah. Before I go to that example, I should say something more. Yeah. So the if functors from C to D are objects and natural transformations are morphisms, then we get the functor category CD. Okay, this is our notation. So functor category as in the collection of functors from C to D as objects and natural transformations between them with respect to, I mean domain and codomain it's clear, but this, yeah, if you have F, then you have alpha, then you have beta, and then you have H, then what is beta alpha? Beta alpha is a natural transformation from F to H. What is its eighth component? It has to be this. Beta sub A, alpha sub A, this composition. No, nothing like that. It's just a map. Yeah, we don't have to specify the domain. And what will be the identity? Identity of this? Like what is this? F to F. We'll call it 1 sub F. And what will be 1 sub F? This particular natural transformation's eighth component? 1 sub FA. Now don't say 1 sub A. 1 sub A is a morphism in category C. We want a morphism in category D. Okay. So this is the data, and here I have defined the functor category. I told you how to write domain and codomain. I told you how to take composition and identity. So this is the functor category. Okay. Any questions? Huh?
What means by
Eighth component, because see, you have to ask when you are talking about a natural transformation, then you are asking for the data. So eighth component, as in the data is given by alpha sub a for each a. So if you just tell me what is the a component of beta alpha, then a is an arbitrary object, so therefore I will know what to do. A is arbitrary, yeah, beta alpha sub a is equal to beta a alpha a. If I replace a with b, another object, then also I will know what to do. It's simply the composition. See, if you are confused, then I should write for each object a of c. Yeah? Yeah, this universality is what I was referring to. Eighth component means this. Okay, so let us look at this example that I promised. So it's the identity functor. So now this is the Singleton as a natural transformation. So I am going to write the category of sets. I am going to write another copy of the category of sets. I am going to say this is one subsets. It is the identity functor on the category of sets, and I am writing the power set functor. Which one, covariant or contravariant? It has to be covariant because I want a natural transformation from identity to it. Identity is a covariant functor, obviously. So therefore I cannot talk about P star here, right? So this has to be the Singleton natural transformation. What does it do? Now I have to give you the component. Well, I already did. So the component of the Singleton map has to go from one subsets applied on A to the power set of A. But what is this? This is just A. And what does it do? It takes a little A and it sends it to Singleton A. So this is your component of the original, component indexed by A. This is a natural transformation. Do you want to check that? Let's do it. Yeah, so suppose there is a morphism A to B in the original category. What do I need? I need one subsets applied on A, which is just A, and then I need something P applied on A. Then I need one subsets applied on B, which is just B, and PB. And then I have a map here which is Singleton sub A. Then I have a map here Singleton sub B. This is a map. What is one subset applied on F? It is just F. Yeah, nothing is changing. And this is the covariant functor. So this is PF. What does PF do? It takes direct images, not inverse images. So what do we want? This diagram should commute. If this diagram should commute, then I should check if I start with some particular A in here and I take two different routes, what will I get? So I start with A, I will get along this Singleton map A, I will get Singleton A. So I need to check PF of Singleton A is equal to Singleton of FA. Is that correct? Yeah. Now this is correct irrespective of what my little a is, irrespective of what my capital A and B are, what my F is. So that's why this transformation is called a natural transformation. Yeah, this is the third level now. Yeah, think about this. Categories have objects and morphisms. Between categories we have functors, and now between functors we have natural transformations. Okay, so therefore usually we think of, like if we are thinking about the category of small categories, let's say, then the categories themselves are called zero objects. The functors are called zero morphisms. The functors are called one morphisms, and natural transformations are called two morphisms. By giving you this analogy, this numbering, I am telling you there is a scope. If there are two morphisms, then there is also a possibility of a three morphism and a four morphism and five morphism, and infinity categories arise in this way. Yeah? So these are morphisms between morphisms, like n morphisms are morphisms between n minus 1 morphisms appropriately. Okay, so if you understood this, then I am going to give you one more example, and which probably most of you won't know, but anyway I have to say this. So this is the Hurwicz homomorphism. So Hurwicz homomorphism is the morphism going from the fundamental group, which is pi 1 of a topological space, to the corresponding homology group, first homology group of the same space. Okay, this was introduced by Hurwicz. I am not going to go into the details, but I will just show you the functors. So first of all, you know that the fundamental group goes from top star to category of groups. Yeah, so this is pi 1, but I can also do it with pi n. It doesn't matter, pi 1 or pi n. The other one, although it doesn't depend on the base point. Homology is a global property, it doesn't depend on the base point. So you have to take the forgetful functor down to top. This is U, forgetful functor. From top to abelian groups, because homology groups are always abelian. So this is H1 or Hn. And then abelian groups include into the category of groups, and this composition is, this whole composition is what our second functor is. And Hurwicz homomorphism, this is called H1 or Hn, like in general. This is a natural transformation between these two functors. And if you know the construction, then you can verify that it is a natural transformation. Any questions? Let's go ahead. I will give you one more tangible example, and that I am sure everybody will understand. So we are talking about real vector spaces. Did we do this example of a functor? Maybe I should do the functor example first. So R vector spaces to R vector spaces, I want to take the dual vector space. Dual vector space, this is a functor. Is a functor. Is it a covariant or contravariant functor? So if I am given a morphism like V will map to V star, then W will map to W star. It's a covariant functor. Let's see. So phi is a morphism from V to W. It's a linear map from V to W. Now can you describe a map from V star to W star? What is V star? Like, what are the elements? Functionals. Functionals means it is home R from V to R. Yeah, this is home R. Okay, now he is saying that we can define a map from, if you take a function from V to R, you can define a map from W to R. Tell me how to do that. Let me draw that diagram for your help. So there is a map from V to R, let me call it F, and there is a map from, yeah, now can you complete this diagram, like go from W to R? No. Yeah, so you can't do this. So on the other hand, if I am given something over here, then I can simply compose it and then I can get a diagram. So automatically this is embedded. Yeah, we don't have to think about it. If you just try things out, then you will get that there is a map here. We call it phi star, which is actually blank composed with phi. It's a precomposition with phi. Yeah, blank is this new map and you have to precompose it with phi. That's our original morphism. So I should ideally write op. So dual space is a functor from R vec to R vec op, and this is a covariant functor. Okay. Now the example of natural transformation that I want to give you is that of the double dual. So I am going to compose this map, this functor with another copy of itself, which I can always do. Yeah, I mean dual is a functor from R vec to R vec op, or equivalently R vec op to R vec. Doesn't matter where I put op, there should be at least exactly one op. Okay, so therefore double dual is valid, and I am going to write this now. So R vect and R vect again, and this is my functor which is double dual, and over here I am simply going to write the identity on this category, identity functor on the category. And now I want a natural transformation from here to here. Can you tell me what it is?
The dual map.
What is the dual map?
I mean, like
If you are given one element of a vector space, evaluation. Yeah, so this is, I mean, I am going to call it evaluation. Okay, and what is its component? If I want evaluation, then I should give its component, and this should be a map from V to V double star, correct? Yeah, because V is one R vect applied on V, and V double star is double star applied on V, and where should it send little v to? Yes, this should be a function which sends f to f of v. It is evaluate at v. Yeah, this you have seen in linear algebra, the double dual and evaluation. So these are always a vector space embeds inside its double dual, yeah, via this map. But this is a natural transformation, and we are going to show that. Okay. So what do we need to show? We have to start with a map. I am just going to call it phi, and then corresponding to that I have a map here from V to V double star, and here I have W to W double star, and here I have map phi, and here I have map phi double star. Here I have evaluation at V and evaluation at W, and I have to show that this diagram commutes. Do you want me to do it, or you will do it as an exercise? Yeah, this is, I mean, you have to understand what's happening. What is phi double star? Yeah, that's a tricky thing to do. I think I will give you one day, like until next lecture. If you can't do it, then tell me. We will do it in the class. You have to verify that this is actually a commutative square. Okay. So now these examples, if you see, then aren't they natural? So far what we saw, you already know about the Singleton map from A to PA. Then if you know enough algebraic topology, then Hurwicz homomorphism is something natural. Then this is natural. In fact, yeah, I mean, I will write this comment. In fact, EV restricted to this I am going to say finite dimensional vector spaces. This also you have seen that for finite dimensional vector spaces, evaluation is an isomorphism, right? So therefore EV restricted to this, sorry, I should say 1 sub R vector FD and double dual is an isomorphism. Okay, that raises a simple question. When we are talking about an isomorphism, which category are we talking about? A natural transformation is an isomorphism. So in which category? Category of functors, functor category. Yeah. So I'm simply going to give you another exercise. Yeah, try to show this. So suppose alpha from F to G is a morphism in CD, show that alpha is an isomorphism. What is the meaning of alpha being an isomorphism here? There exists a morphism from G to F. Yes, the beta such that alpha beta is equal to identity. Identity on what? No, alpha beta is identity on? No, not C. Yeah, this is where things get complicated. Alpha beta is an? Okay, I am just going to write it for your help. Yeah, i.e. there exists beta from G to F such that alpha beta is equal to identity on G and beta alpha is equal to identity on F if and only if alpha A is an iso for each A in object of C. So you can check whether the natural transformation is an isomorphism or not based on the checking of the individual component morphisms. Okay, very useful criterion. Yeah, if these properties are true, then we say that alpha is a natural isomorphism. there is nothing unnatural about it. Yeah, everything works the way it should. Either it works or it doesn't. Yeah, in category theory, the idea is that if something works, then it should be obvious, it should be staring at you in the face, or it doesn't work. Either things are obvious or they are impossible. Okay, so this is called a natural isomorphism. I'm also giving you a definition. Okay, so today's lecture started with a discussion of equivalence between categories which preserve and reflect properties of categories. They are not different. Categorical properties are the same, number of objects in there doesn't matter, just the properties matter. Now we are ready to give a definition of equivalence of categories. So let's do that. Say that categories, maybe I should say given categories C and D, say that the data of functors, now please pay attention, there is a functor f going from C to D and another functor g going from D to C, together with natural transformations Okay, I am going to use some specific notations. Yeah. So usually, if you have observed that I am using specific notations for everything. Categories are always curly letters, calligraphic letters C and D. Then functors are always F and G. H, capital letters. Objects are Roman capital ABC, ABCD. Then morphisms are always lowercase fg, h. Yeah? And Greek letters are reserved for natural transformations. So I am going to use two particular natural transformations and their meaning will be clear later on in the course. So together with natural transformations eta from 1 sub C to GF and epsilon from Fg to identity is the data of an equivalence of categories if eta and epsilon are natural isomorphisms. Okay, perhaps a long-winded definition, but what we are saying that C and D are two categories, they are equivalent if there are functors in opposite directions such that their compositions, yeah, GF and FG, we are not claiming that the compositions are equal to identity. Yeah, if it were functions, then we would have claimed that they are equal to identity functors. But equality is an evil notion in category theory. Yeah, we don't want to use it. We rarely use equality in category theory. Everything is replaced by an isomorphism of appropriate kind. Now, what is the isomorphism in this case? The natural transformations are an isomorphism. Now, when you look at this definition, what comes to your mind? What is the first thing that you have seen and which is similar?
Homotopy equivalence.
Exactly, homotopy equivalence. Yeah, there are two spaces given, x and y. Then you have a map f going from x to y, map g going from y to x. Both are continuous, such that GF is homotopy equivalent to identity and FG is homotopy equivalent to identity on y. Now, the only difference from that thing to this thing is that here we have for some reason chosen some direction for this homotopy equivalence. I mean, these are natural isomorphisms. Okay? Natural isomorphism means in the opposite direction also you have an isomorphism. But we have chosen a direction that eta always goes from 1 sub c to GF and epsilon goes from FG to identity 1 sub d. The reason for this will be clear later in the course, but for now you just accept, I mean we might have as well started with 1d to FG, like epsilon inverse. Yeah, it doesn't matter. For this definition it won't matter. Is this okay? Right. So this is the definition of equivalence of categories. Yes, Suyesh.
So these are natural isomorphisms, so it does not matter. So there is no essential difference with the homotopy.
There is no essential difference as far as equivalence is concerned, but we are going to generalize this situation in the future, and for that we need this direction of natural transformations. Yeah, in that case these won't be isomorphisms, and then the direction will matter. Any other questions? Okay. So this is equivalence of categories. Let's look at some examples of equivalence of categories. The first example is something that you already saw, so I am just going to repeat it. So start with this. Finite dimensional real vector spaces. Real is not really important. You can start with any field, and I am taking its opposite category. Is there a functor from first one to the other one? Which one? Star, dual. And from this one to this one also there is the dual. Okay, what is eta in this case? What is eta? Eta goes from 1 sub r vect fd to double dual. Evaluation is EV, and what is epsilon? No, it is evaluation inverse, because it goes from FG to identity. So FG would be double star, double dual, and then double dual to this, so that will be evaluation inverse. But evaluation is a natural isomorphism. We have seen that for finite dimensional vector spaces. So therefore, this data will tell you that the category of finite dimensional vector spaces and the opposite category, they are in fact isomorphic. Very interesting result. Yeah, I mean, think about it from just a purely linear algebra perspective. We are formally reversing the arrows, linear maps. Just change their domains and codomains, it doesn't matter. We still have an an equivalence of categories. Okay, so let's look at another example. Suppose P is a pre-ordered set. This was our original motivating example. preordered set, and P bar is the posital reflection. Yeah. Then do we have a map from P to P bar? Projection? Yes, correct. There is a simple map. I mean, this is a set, yeah. So what are the, these are two preordered sets. Yeah, poset is also preorder. So what are the functors between them?
I mean, the projections.
No, projection is not the answer. Functors are monotone maps. Monotone maps. Okay, so what is a natural monotone map from P to P bar? You take an element,
We assign it its equivalence class.
assign it to its equivalence class. Okay, very good. Where what is this equivalence relation?
I mean, if
Less equal, intersection, greater equal. Okay. Now, do we have a map in the opposite direction? P bar to P. The elements of P bar are equivalence classes. What will you map it to in the backward direction?
I mean,
Choice,
it's-
we can choose representation.
Exactly. We have to choose. So, using axiom of choice, we can construct a map backwards. It will be some kind of inclusion. This will be a surjection, this will be an inclusion, and this is thanks to axiom of choice. Yeah, for every equivalence class, we choose one element from that. So, thanks to axiom of choice, we can always go backwards, and then you have to choose the, and what will be the eta and epsilon?
So, I had a question.
Yeah.
So, you said that category theory can be seen as a foundation for set theory.
Uh-huh.
So,
Foundation for set theory, I did not say that, an alternate foundation
yeah, alternate foundation
for mathematics. Set theory is the most commonly accepted foundation. Category theory can be seen as an alternate foundation for mathematics.
Okay, so it's not, I mean, but, okay, I also saw that it is expressed as a foundation for set theory. I mean,
And that will be something different.
frameworks,
No, why? How is it related to this?
because you said axiom of choice and I just
Yeah, because I am talking about preordered sets. And I am talking about a small set. So therefore, if I have to choose from possibly infinitely many equivalence classes, I have to choose one element each. Then I have to use the axiom of choice. So I have to go back using axiom of choice. Yeah. So here I'm already assuming set theory in the background. Yeah. Some universe of set theories. Okay. So now what will be eta and epsilon? They will be equalities or isomorphism. So let me call this particular map F and let me call this one G. Okay. So Fg will be equal to identity on P bar. So therefore, this is just clear. And what will be GF?
Like an isomorphism from
Yes.
to the representative.
Right. GF of P is isomorphic to P for any P. I mean, let me change it for any P in capital P. And this choice of morphisms will give me a natural transformation which happens to be an isomorphism. Because of the property we said, a natural transformation is an isomorphism if and only if each component is an isomorphism. So therefore, that will give me this property. Okay, so this is how we are describing. In the original example, if I go back, I think that was 16 or 17. Yeah, in this example, these are naturally these are equivalent posets. How will you go from here to here? You will send B and C to the equivalence class of B and C. Yeah, this map is clear. A will go to A, B and C will go both map to the same element. But while coming back, I need to make a choice. A will go to A, but for B equivalent to C, I have to make a choice of either B or C. So that's what equivalence does. It doesn't care about isomorphic objects. You can go back to something isomorphic to the original. You don't have to go back to exactly the same place where you started. Yeah, that's the whole point. In both directions you can do that. Okay, so we are here. Okay, so remember this axiom of choice. I am going to give you some more examples from different areas of mathematics. Okay, the first one, in algebraic geometry, the opposite category of locally ringed spaces is equivalent to the category of commutative rings. Okay, if you don't know what these things are, don't worry. But such a thing is, a couple of things about notation here. Yeah, so I will write it in red, that if C and D are equivalent, we write C equivalent to D. Yeah, this is the first thing. This is the notation for equivalence. Isomorphism is different. Yeah, isomorphic means up to equality. Then we write C isomorphic to D. Then eta and epsilon in this case are equalities. Yeah, which is an evil notion, but sometimes it will happen. And if C op and D are equivalent, then we say C and D are duals, dual equivalent. Okay, so dualities in mathematics, they come from this particular notion. So logic has got several dualities. Logic has several dualities under the name of syntax semantics dualities. And sometimes you don't even imagine that there is syntax and semantics coming in, but in propositional logic, for example, the syntax part is given by the category of Boolean algebras and Boolean algebra homomorphisms between them, and the semantics part is given by the so-called stone spaces, and these two categories are equivalent, like one category is op equivalent to the other. So what are stones? Boolean algebras, they are generalizations of power set where you have union, intersection, complement, and least element, highest element. Okay, stone spaces, these are compact Hausdorff spaces with and totally disconnected spaces. Totally disconnected means only singletons are the connected components. Okay. So compact Hausdorff and totally disconnected spaces. And stone spaces, basically they talk about the space of ultra filters of a Boolean algebra, and you can recover it from the Clopen sets, recover the Boolean algebra from Clopen subsets of the stone space. More generally now, if we want to go slightly outside, then this particular category will also be important. The category of compact Hausdorff spaces. So I'm just going to call it K-Haus. Yeah, compact Hausdorff spaces is dual equivalent to the category of C-star algebras, commutative C-star algebras with identity. So operator algebras, C-star algebras. So the point of all these examples is to show that equivalence is a very fundamental notion. It's widespread throughout mathematics, and dualities also are widespread. So you can see there are different types of things at play. Yeah, like there are different areas of mathematics coming together, are related via certain dualities. I am not going to describe what these functors are, etc., but at least to give you an idea that the reach of dualities and equivalences is a lot. Another thing, yeah, for rings R and S, let's say commutative rings.
What is K-Haus?
Yeah, that's compact Hausdorff spaces. For rings R and S, yeah, if you consider the category of R modules, left R modules, and then you consider the category of left S modules, one simple example, yeah, then this category is equivalent to the category of R cross S modules.
What is that product of?
Product of categories. I mean, you just take pairs of objects and pairs of morphisms, pairs of identities. Composition is component wise.
Okay.
Yeah. So nothing is odd about it. Okay. So there are so many examples. I can add more, but let's not just keep doing that. Instead of that, I want to talk about one way of characterizing this particular equivalence. So this will be the first theorem of our course. Okay. So given categories C and D and a functor f from C to D, f is part of an equivalence of categories. I am going to write its explanation, i.e., there exists G from D to C and eta from 1C to GF, epsilon and and isomorphisms eta and epsilon. So this data is suppressed at the moment. Okay. So this data exists for a given f, if and only if. Okay, sorry, I should add something. Yeah, this is very important. Given locally small categories C and D, if and only if f is faithful, full and essentially surjective on objects. And this is the statement that we are writing assuming axiom of choice. Okay, so this is given, like without axiom of choice we can't prove this theorem. So this is a test for axiom of choice. Sorry, test for equivalence of categories. And I think you won't be surprised that axiom of choice has entered our discussion, because just 2 slides ago we actually used it and we need it for exactly the same purpose. So what we are saying, look at this, that there is this data of f, g, eta and epsilon, those 4 things, but we don't need all of them. We just have to check some properties for one functor, namely that it is faithful, full and essentially surjective on objects. Now I should first describe what these things are. So this is a definition, yeah. F from C to D is a faithful functor. I already motivated them to you last time. Is a faithful functor if there is an induced map, yeah, from home C AB to home C, home D, FA, FB. Okay, so because every map, every morphism from A to B goes to a morphism from FA to FB. That's what the this functor does. So it takes a morphism F and maps it to FF. Yeah, this map is injective for all AB in objects of C. So faithful functor is nothing but it's injective on home sets. So if there are 2 parallel morphisms and they are distinct, then they will be mapped to 2 distinct parallel morphisms. Now you can imagine what full means. This has to be surjective, very good. So when I am saying it's fully faithful, then what do I mean? It is bijective on home sets. And the final thing that I haven't defined is that f is essentially surjective on objects, so that I have to describe. So f from C to D is essentially surjective. I mean it's as good as surjective but up to isomorphism. If for each D in object of D, there is some C in some object of C such that FC is isomorphic to D. Get it? FC is isomorphic to D. Every object of D is isomorphic to something in the image. So if you remember what I said at the beginning of equivalence of categories, I said that you don't have to worry about how many isomorphic objects there are. So just look at this. We are saying that we don't really worry about how many objects are there, as long as from each isomorphism class I am hitting, the functor f is hitting at least one object. and locally the structure is a bijection. So that's given by fully faithful. So I think you are quite, the statement is not surprising once I have explained all the terms. Yeah, that whenever there are two objects, then the home set is transferred bijectively to another home set, and from each isomorphism class we are choosing this. So maybe there are, so let's imagine that there is one connected groupoid whose identity, whose endomorphism, where endomorphism of any single object is isomorphic to, let's say, the group of integers. Okay. Then there is another connected groupoid, which means there are, every morphism is an isomorphism, where also the endomorphism of any object is isomorphic to the group of integers, additive group of integers. Now it doesn't matter how many objects there are, maybe this is a set, maybe this is not a set, or maybe this one contains only one object, this one contains 5 objects, but this theorem is going to tell you that they are equivalent. They are equivalent. Yeah, we don't need isomorphism. Those categories are not isomorphic. Like object to object bijection is not what we expect. But connected groupoids are as good as just a single group, and that's what we are saying here. From each isomorphism class, we have chosen one. From each isomorphism class, we have chosen one. And if there is a bijection between isomorphism classes on both sides, and on top of that the functor should be fully faithful, then we are equivalent. Yeah, the number of copies of isomorphic copies of the same object, that's irrelevant. That's all we are saying here, and that's something we always need. Yeah, for example, we think about this. If you remember, there was an example where we were talking about this matrices. Yes, this one, number 10. Yeah, look at this, finite dimensional real vector spaces with a fixed choice of basis. We are sending it to the category of matrices. What are the objects here? Natural numbers, and the morphisms are matrices. Okay. Now this is actually an equivalence of categories. This is an equivalence of categories. Why is that so? Because, I mean, if you want to see it directly, then also you can see it from mat R to the other side. What do? You have to send one particular n to some specific vector space and some specific choice of basis. What is that called? Specific choice of basis? Huh? Standard basis, right? Ordered like 1 0 0 0, then 0 1 0 0. So you send it to R to the power n with the standard basis. Then you look at this composition. You start with one particular vector space of dimension n and a choice of basis. Then you just drop it down to its dimension and you come back to R to the power n with the standard basis. Now this original v comma b and this Rn with standard basis, they are not equal necessarily, but they are isomorphic. Yeah, and you can also use the theorem to conclude this. Right, so that's what I mean. Now I'm going to give you some homework. You have seen many examples of functors. So you should look at, you should check which examples are full, which examples are faithful, and which examples are essentially surjective. Okay, and let's stop here.